I have an example using Bernoulli's principle, which is conservation of energy during the flow of a fluid and a relationship that holds along a streamline. We have a water tower open at the top, and unfortunately it has a hole that's developed in the bottom. And our task is to determine, as that hole is opened up, where along the ground is the water going to land at first. Applying Bernoulli's principle, I want to think about a streamline. Let's say it's going to start there at the top, the open air part of the water tower, and it's going to have some shape that carries it down through the hole. And we're going to call that our bottom state, labeled with a B. So streamlines are mathematical curves, so they're not necessarily real objects, but imagine that I have a massless tracer particle that just travels along with the fluid as the fluid flows. And the flow of the fluid will be such that streamlines can't cross one another. So for every point at the top of this water tower, if it is allowed to let all the water flow out, there must be a path that would take every point on the top out through the hole at the bottom there on the side. Okay. So that's the 2 points that we're going to apply conservation of energy to via Bernoulli's principle. So relate our state at the top and the state at the bottom. I'm going to just write out Bernoulli's principle. So conservation of energy is going to say that the pressure at the top plus a half rho v, so the speed at the top squared, plus rho g, and the height there at the top. So we have pressure contribution, kinetic energy density, half rho v squared, and a gravitational potential energy density, rho g y, for the height. So that can't change along the streamline. So that has to equal pressure at the bottom plus a half rho v at the bottom squared plus rho g and the height at the bottom. Alright, so we have some simplifications that we can make. The speed at the bottom could be significant, but if you just think about like the ratio of those two areas in the continuity equation, this is a little itty bitty hole, and that's the area at the top is the whole water tower. So from the continuity equation, the speeds of the flows are going to be such that the speed times the area is equal. So it's going to be much faster speed for the much smaller area here at B, and a much slower speed for the much larger area at the top T. So it's going to be so slow at the top that we're going to take this to be approximately 0. They ask, what is the pressure going to be at the top? That is the atmospheric pressure. And also, just right outside the hole, that's also atmospheric pressure. So the pressure difference is not going to have any influence on the flow. And P at the top, P at the bottom are going to cancel out. So terms that survive, going to have 1/2 rho speed at the bottom squared, because it's the speed at the bottom that we need. And then everything else is moved over to the other side. It's going to be rho times gravitational acceleration, and it's going to be y at the top, move this over, minus y at the bottom. And if we want, we can just call that delta y. Alright, it is the same mass density for the fluid on both sides of the equation. So that is going to cancel out. So rho cancels out rho. And we'll have an answer that then looks very familiar from whenever we've applied conservation of energy before. The speed at the bottom is going to be 2 times g times the change in height, all square root. So the fact that this is a fluid flowing is not having any impact on our answer. It's just what we would get from conservation of energy alone for a particle that falls through a distance delta y. Working that out to get an answer, we get 14 meters per second. Okay. So now we're going to have projectile motion. The initial velocity of the stream is going to be at 14 meters per second. It's horizontal. We want to find out where it actually lands. So how long does it take to fall 15 meters, starting from rest? And it's from rest in the vertical direction, not in the horizontal. So delta y, v initial along the y direction, delta t plus a half acceleration along the y direction, delta t squared. And it starts off with only a horizontal velocity. So it goes to 0. This lets us calculate how long the stream is in the air from the time it leaves the hole to when it hits the ground. So 2 delta y, the y component of acceleration, is going to fall through 15 meters. And acceleration due to gravity, if up is the positive direction, it's minus 9.81 meters per second squared. And that gives us 1.7 seconds for the time for any part of the stream to be in the air. And where does the stream land at? It's going to be at a horizontal position x equal to v initial x delta t, which we have 14 meters per second and 1.7 seconds. It's going to give us 23.8 meters, or keeping just two significant figures, 24. And as the water level in the tower starts to drop, the change in height is going to be less and less. That's going to make our speed of the fluid be less and less as it leaves the hole. So eventually, by the time it's all emptied out, it's just going to dribble out. You can also view that as this fluid in the bottommost layer within the water tower. That layer of fluid is having to support the weight of all of the fluid above it, and therefore the pressure is higher at the bottom to let the fluid be in approximately hydrostatic equilibrium. As the fluid level drops, the pressure at the bottom is going to decrease, and so the fluid is going to come out at a slower speed. So everything with how pressure changes with depth within the fluid is also there in Bernoulli's equation.